This is going to be a shorter presentation. We talked about MVAPitch, what its various knobs are, what its various features are in the previous talk. So, in this talk, we'll be talking about the OSU Microbenchmarks. Now, OSU Microbenchmarks is much more popular. It can be used by any MPI library, any MPI installation. It is part of various national procurement suits like the Trinity benchmarks from NERSC. So it is used by a lot of organizations to see if a particular machine is like up to slack, and it has a lot of features. So over the last 2 to 3 years, we have been doing a lot of active development on the OMB side. In the 22-23 year, we had made 4 separate releases of OMB with various feature enhancements and moving up to the latest MPI specifications. The latest release of OMB is the 7.4 version. So this kind of summarizes all the updates and newer features that we have added to OMB since last year we were here. So we have added support for AMD's ROCm like RICL benchmarks for both point-to-point and collective operations. Since the MPI standard has evolved into 3.1 and 4.0 and 4.1, we have added support for newer MPI primitives like persistent collectives. Based on feedback from one of our users, the Lawrence Livermore National Labs, we had added newer benchmarks to measure network congestion. So this is a basic fan-in, fan-out benchmark. To do let's say, view the numbers better, we had added support for custom percentile values. We have a lot of support for logging validation failures. We have added new collective benchmarks like reduce scatter block and the non-blocking version of that. So since MUC 23 in the last year, like 23-24, we have made 2 releases, V7.3 and 7.4, and this kind of summarizes all the features that we have been able to incorporate in them. And these kind of summarize the features like network congestion measurement, log for validation, basically RICL point-to-point collective benchmark, so on and so forth. So now I'll hand it over to Nat to go into a bit more details about how we have support for some of the other benchmarks like derived data types and things like that. So Nat, do you want to take over?
Okay, so as Hari mentioned, we did recently add support for derived data type benchmarks. So the main feature with this is that even if you aren't really familiar with how derived data types are actually implemented within MPI, the options for them are pretty straightforward. So if someone gives you a description of a derived data type, you can implement it in, or you can test it out in any of these different ways. So either as a contiguous, vectored, or indexed implementation. And all of those are supported. And our hope is that even though derived data types are still rarely used feature of MPI, this will allow users to test them out and see how they're performing on their system and potentially start using them as HPC applications advance. So this shows you the output of a DDT test. So we can see in addition to the size, which is going to show us the like standard message size, how many of them we're transferring, the transmit size is going to show you the actual number of bytes that includes. So for this data type, right, so this is good. The size over here is going to be the maximum size of the transmit. The transmit size is going to show you how much was actually transferred. So in this case, we're not actually transferring anything for these smaller types because they're too small to make an entire data type. And then we can do that either, so as shown in the options, we can either do that on the command line directly or by building it in a file that is then read in by OMB. And you can find more details on these in our user guide for OMB as well. We've also added a plotting summary that allows you to do some basic graphs of OMB performance, including our latency and bandwidth tests. And you can do that directly from OMB instead of having to pipe these into like a Python script and then plot them with Python. So this uses the GNU plot utility to plot them directly. If you don't have that in your basic path, you are going to have to put it into your configure. And we'll also use ImageMagick to convert it to a PDF, which can be very nice for showing performance numbers on a given system. And this is enabled with the -G flag. So these are some examples of performance plots. So we can do it in the terminal, but for better readability, we can do 2D and 3D plots using GNU plot as well. And so this can be useful for seeing like, all right, we have these messages spiking here on certain iterations. And then you can go in and look at why are messages spiking every 100 iterations and start to debug what's going on your system. We also have PAPI hardware counter support in OMB. This is the Performance Application Programming Interface, which can be used to collect various hardware counters on your run. So you can enable that with the appropriate configure flags listed here, and then you can list various PAPI events that you want to profile and tell it where to print those. More details about those, the types of events that are supported by PAPI can be found in its documentation. So here again is an example of the output that you get. So we can see the various events. So like L1 here is going to be your L1 cache hits, and it's going to tell you how many of these are occurring at each rank on your all reduced run and for each message size. So you can see how you're performing in different metrics as the benchmark runs. We've also recently added support for neighborhood collectives in OMB. So this is a type of collectives. Once again, it's a relatively new feature of the MPI standard, so not in a lot of use in applications yet. But as people start to move forward with some of the newer MPI features and actually start taking advantage of all the features that 3.1 gives them, it's going to be worth using to see how these perform on a given system, since they're such a new, or not new, but relatively underutilized element of the standard. Having a benchmark for them helps us see where they might be useful. So once again, some sample output of our neighborhood collectives, how we run them. And again, they can be set up in a text file to try and simulate more complicated behavior without you having to type out a million characters on the command line. Once again, more specific details of how we use these can be found in our user guide. We also support MPI built-in data types. So older versions of OMB would pretty much just use MPI char types for most communication collectives and just MPI ints for reduction-based collectives. We have this available now to switch between different types so that you can see the performance of your MPI library on more than just single byte char characters if you want to test how it's performing for floating point or other data types that are built into the MPI standard as opposed to the derived data types. And you can also use the -T all to test all three supported data types and see how it performs across different MPI primitives. At the request of users, we've also added the customized percentile values so that you can see different aspects of the performance. So we've supported the full option for some time, which shows the min and max latency as opposed to just the average latency. But this allows you to set custom percentiles to see different aspects of your performance profile. And then we've also, as Hari mentioned, at the request of Lawrence Livermore National Laboratory, added some network congestion benchmarks, which will allow you to do fan in and fan out bandwidth tests. So in this case, the fan out test is going to have one sending node sending to a customizable number of receiver nodes, and fan in is going to be the opposite. Many sender nodes sending to one receiver, and multiple processes are available on each of those nodes. So this allows you to test the performance of your system when the network is being saturated, either incoming or outgoing. We've also added support for MPI in-place collectives. So many collectives support an in-place option, so we can test that as well, which is useful for validation. Shouldn't affect performance in too significant of a way, but it is good for using for validation. And we've also started adding support for some MPI 4.0 features. So right now, we currently support the MPI sessions model. So for those of you who are not aware, MPI has support for an alternative to COM World, which is what we've been using for a long time. And that's the sessions programming model. And that allows you to create a session, close the session, initialize a new session, and generally escape the hard and fast COM World setup. So this, again, is mostly for validation to see that your application point-to-point and collective performance is the same when using COM World or MPI sessions. As with a lot of these newer MPI features, this is going to become more and more important as people start to experiment with the newer MPI 4 features. And then we also allow for the setting of the root rank so that you can see if your application is being impacted by where the root rank of rooted collectives is. So you can either fix it to a single process, right? Your default is typically going to be 0, but you could try moving that to a different rank, or you can rotate it through different ranks throughout the run, which allows you to test the performance of different routes being used. We've also added RICL support. So this is basically the ROCm version of Nickel. It uses a very similar interface, and we support benchmarking that as well. So you can compare the performance of RICL collectives to MPI, as well as MPI 4.0 persistent collectives, which, again, mostly for validation, but as more work gets done on enhancing their performance, we want to see what kind of benefits they can give in terms of performance gain. And then we also will now provide a output of what validation failures occurred if your test fails validation. So this can be really useful when debugging an MPI library. It's mostly targeted at MPI developers so that they can see what is failing if their MPI implementation is failing validation tests. Future plans for OMB include adding new OpenSHMEM benchmarks for bandwidth, so you can compare OpenSHMEM performance to MPI performance in point-to-point operations, adding Intel GPU support through Intel One API and SYCL, so that we can test Intel GPUs just like we do with AMD and NVIDIA, add accelerator support, so GPU support for neighborhood collectives, and adding partition point-to-point benchmarks to measure potential overlap capability when using partitioned point-to-point operations.
I think that's all the